Good afternoon. People are filtering in, very much appreciated. Thank you for joining the Distinguished Scientist Fellow ceremony. In the lecture that features Dr. Lois Curfman McInnes from Argonne National Laboratory. For those that don't know me, I'm Linda Horton. I'm the Associate Deputy Director for Science Programs here in the Department of Energy. And I am pleased to welcome our many distinguished guests, including Dr. Paul Kearns from Argonne National Laboratory, and the leadership that's here from the Office of Science. Ceren Susut, J.P. Elaine is here as well, and so many others. So thank you all for joining us in person. And I know there are many people online who have joined these lectures because they're such an exciting event scientifically. So, and then of course, I'd like to welcome our lecturer, Lois McInnes, and her family and invited guests who have joined us both here as well as online. Today we are celebrating Dr. McInnes's accomplishments in computer science and her selection as a 2024 Office of Science Distinguished Scientist Fellow. Before we hear from Dr. McInnes, I'd like to first welcome Paul Kearns to the podium to give some remarks. Paul?
Thank you very much, Linda. Thank you. Let me also say thank you to Harriet Cohn, really, for the privilege of being with you here this afternoon to help present the 2024 DOE Office of Science Distinguished Scientist Fellowship Award. The creation of this award in 2019 was a visionary step for the Office of Science, providing a pathway to recognize superlative senior scientists at the national laboratories and maritime port research. This is a remarkable opportunity for Lois, and this year's we're selected by the peers of this recognition. Recognizing them really is a testament to their exceptional contributions to transformational advances in science and technology. As many of you know, Lois has set a high standard in the scientific community. Over the past 30 years, she's developed innovative algorithms and software serving the leadership roles for the exascale computing project, pioneered exciting advancements in high-performance computing, computational science and engineering, and applied mathematics, leading to notable progress in many fields of science. Her work has not only advanced scientific discoveries, but it also has inspired many emerging research across not only Argonne, but also other national laboratories and throughout the broader scientific community. We're fortunate that Lois joined Argonne as a DOE's Distinguished Postdoctoral Fellow after earning her Ph.D. She then became full-time staff shortly thereafter, focusing on the developing scalable methods scientific computing. Today, Lois's experience and dedication has been widely recognized. She was the deputy director for the science technology area in the exascale. She also provided leadership in initiatives like the IDS project, better scientific software. She has won numerous awards and honors throughout her career. One of my most memorable conversations with Lois was when I called her to let her know that she was selected as an Argonne Distinguished Fellow at the laboratory. So honor held only by about 2% of the scientists really on the laboratories. Fun time to hear firsthand about her research and her career and her vision of what was next. It's so exciting. So at each career step, she highlighted her commitment to fostering a more collaborative community. Many other contributions also underscore her impact on the field. Speaking more broadly, to further strengthen U.S. scientific leadership in supercomputing, we need more researchers like you. All of you are well aware that there is a fierce race to build faster, the fastest supercomputers and the most advanced AI models. DOE National Laboratories have the three most powerful exascale computers in the world, including Argonne's Aurora, which is now open to researchers. However, we know that the global competition is in the rapidly evolving field of AI is formidable and will only continue to accelerate. Yet its potential benefits for humanity are extraordinary. And here's what sets us apart as a community in this pursuit. We bring together some of the world's brightest minds, most powerful computing systems, and massive scientific data sets to advance pivotal discoveries and transformational breakthroughs. Our science community encourages partnerships and outreach, which allows us to tap into each other's expertise and resources. These collaborations are really crucial in modern science and engineering. As a community, our legacy of pioneering scientific leadership is truly unrivaled. We engage with the best and the brightest, we lay the foundation for subsequent advancement. That's why I'm fully confident that people like Lois we will continue to help the U.S. revolutionize scientific discovery. As Lois embarks on this new chapter with this fellowship, we look forward to seeing how she will explore the impact of emerging AI technologies and foster collaboration in developing cutting-edge software applications. Her work will continue to shape the future of scientific computing in an AI-driven world. I look forward to hearing our upcoming lecture, and certainly will encourage us to continue to unlock new scientific frontiers for our industry. Congratulations once again to Lois on this well-deserved honor. Her dedication and leadership inspire all of us. So thank you very much.
Thank you, Paul. I especially appreciate you coming to join us today in person. So before we present Dr. McInnes with her award, I'd like to say a few words about the program, the Distinguished Scientist Fellows Program, as well as complement what Paul has already said about your many accomplishments. These awards honor the extraordinary scientific achievements and professional service records of the senior scientists at the DOE National Laboratories. The fellows were nominated by their colleagues, endorsed by the lab directors, and selected through a very rigorous peer review process. They exemplify excellence in their field and represent the best that DOE National Laboratories have in terms of science, mentorship, and service to the broader community. Fellows receive $1 million in direct funding for support of initiatives for the future that enhance and sustain excellence in the Office of Science Research through collaboration between academic institutions and the laboratory itself. Since its inception in 2019, the Office of Science has now recognized 17 Distinguished Scientist Fellows, and Lois is one of 4 for 2024. I am now pleased to provide a few words about today's honoree and speaker. Dr. Lois Curfman McInnes is an internationally renowned computational scientist and, as Paul said, a distinguished fellow at Argonne National Laboratory. She is celebrated for several sustained contributions to the field of high-performance computing, including developing numerical algorithms for the parallel solution of large-scale scientific applications, developing toolkits now used worldwide by many scientists in many different fields, and designing common component architectures. These accomplishments impact areas at the heart of DOE's mission to ensure America's security and prosperity through transformative science and technology solutions, and have been instrumental in advancing the mission of the Advanced Scientific Computing Research Office for scientific discovery using parallel performance, using high-performance computing. I betrayed my roots when parallel computing was new. The DOE is a world leader in the creation of cutting edge and enabling technology for computational science and engineering. As a nation, we have invested billions of dollars in computing hardware development. But as those of us in the field know that the hardware is not very useful without the software that enables us to do the science. Historically, computer scientists wrote software codes to solve specific scientific problems that were specific to a particular computing architecture. And I remember the days when the newest postdoc to join the group was the one that got to move the software from computer that we have today to the one that was coming in that we were going to use tomorrow. So at that time, codes were highly customized, the software platform became closely coupled. And as the architectures changed and advanced, investments in the software could be lost or require investment of many man-hours of labor to move them forward. Dr. McInnes's efforts to build large collaborations to develop flexible software libraries and frameworks address this problem head on. Her work has helped unlock the potential of exascale computing, making it possible to tackle complex scientific challenges more effectively over time. As we have already heard from Paul, Dr. McInnes has provided critical leadership and technical contributions to several DOE projects and collaborations. One of her most outstanding accomplishments is her work with others on the Portable Extensible Toolkit for Scientific Computing. With thousands of users worldwide, this is regarded as one of the most successful long-term software projects that have been supported by the Department of Energy. Today, federal agencies and leaders in industry commonly employ PETSI in areas such as accelerated design, astrophysics, plasma physics, quantum chemistry, quantum chromodynamics, and subsurface flow. Another accomplishment, the Extreme Scale Scientific Software Development Kit, grew out of the Exascale Computing Project and interoperable design of extreme scale application software or ideas. Much easier to say. It is a coordinated effort across some of the most widely used scientific libraries and enables turnkey use of crucial libraries with guaranteed compatibility and impossibility before the beginning of the ideas project. Dr. McInnes has been recognized by her peers through fellowships, awards, honors, and professional leadership positions. She's a fellow of the Society for Industrial and Applied Mathematics. For work with her colleagues, including Dr. Barry Smith at Argonne National Laboratory, she received an 100 Award and a DOE Orlando Lawrence Award, a DOE Lawrence Award. And as a member of her nomination team put it, her leadership and service to several professional societies is legendary. Dr. McInnes has always looked beyond her own research towards the scientific community at large. This commitment can be seen in her efforts to support, train, and recruit emerging scientists and engineers throughout her career. Awards like this are based on accomplishment, but they also have a future dimension because they designate an awardee as a role model for others. Dr. McInnes's work exemplifies the power of collaboration, innovation, and dedication to advancing scientific discovery. She clearly represents all the attributes of an Office of Science Distinguished Scientist Fellow: commitment to science, leadership, and service. We are pleased to honor her today. Now it is our pleasure to present the Distinguished Scientist Award to Dr. Lois McInnes for exceptional accomplishment in algorithms and software, leadership in major projects, including the scientific discovery through advanced computing, or SCIDAC, and the Exascale Computing Project, promotion of scientific productivity and software sustainability, and for the outstanding efforts to broaden participation in high-performance computing and related science and engineering. I'd like to welcome Dr. Ceren Susut, Associate Director of the Office of Science for Advanced Scientific Computing Research, to come forward to present. And then Dr. McInnes, please join Ceren. Everyone join me in congratulating Dr. McInnes with a round of applause as they I followed my instructions well. Thank you, Ceren. And again, congratulations to Lois. And now, what we've all been waiting for, everyone, please join me in welcoming Dr. McInnes to the podium for her lecture.
Thank you so much for the kind introduction. I am incredibly honored to be here, and I really view this award as a recognition of the strong tradition of excellence in advancing scientific computing at my home institution, Argonne, and throughout the DOE lab system. The Department of Energy has always been a leader in computing innovation. As shown here, computing is now broadly recognized as a third pillar of science, along with theory and experiment. And the Department of Energy's funding for basic research in applied math and computer science broadly underpins discovery throughout the computing sciences. Shown here are just some of the applications within the Department of Energy's exascale computing project, recently completed, and were a broad collaboration across science domains and offices. Of course, it's important to step back and think about the software that underpins these science advances. This diagram shows just some of the phases in modeling, simulation, analysis, and optimization that are involved in scientific computing. And as teams are working to advance their science, they typically need to leverage technologies, reusable libraries and tools that are themselves developed by a variety of different groups. So it's important in order to advance next generation scientific challenges to consider advances needed in scientific software ecosystems. Broadly speaking, an ecosystem is a group of independent but interrelated elements that comprise a unified whole. And it's the interactions and relationships among those different elements that enable the ecosystem to function, and in some cases to thrive. This is a picture of one of my favorite parts of an ecosystem, math libraries. These in particular are the math libraries within the E4S or XSDK, showcasing independent libraries developed by a variety of teams throughout our DOE community that together are advancing algorithms and analysis and are being designed to fully exploit the computing power of our leadership computing facilities. Shown here are Aurora, Frontier, and El Capitan. So today, I'll touch a bit more about background history and challenges in architectures and applications. Then I'll discuss my own work in advancing applied math research, numerical libraries, touch on broader community issues in scientific software ecosystems, and then discuss some next generation challenges and opportunities. As I progress through this, I'll speak about my own roles in various projects and programs, and shown below here are just some screenshots of scientific literature in some of these areas. So first, I'll provide a few remarks about my own background, which helps provide a context for my role in this work. As mentioned, I received my undergraduate degrees in math and physics from Muhlenberg College. I'm from a small town in Pennsylvania. Muhlenberg is also in Pennsylvania. I received a Ph.D. in applied math from University of Virginia and had the privilege to spend summers working at NASA Langley and at Argonne. Being a student visitor at Argonne, changed my life. I absolutely loved existing in the lab environment, communicating with other colleagues, working in the multidisciplinary context of both the particular lab Argonne, but also the broader lab community. And I've been there in one form or another ever since. At the same time, I do also have a family who've been wonderfully supportive throughout my career. This is a picture of my husband and 2 daughters taken about 15 years ago. So I sincerely thank my sponsors, the Department of Energy, especially the Office of Advanced Scientific Computing Research, my collaborators and communities, and I'll talk more about all of these as we progress. Much of my work in numerical algorithms and software is encapsulated within the Portable Extensible Toolkit for Scientific Computing, PETSI, and the related Toolkit for Advanced Optimization, TAO. Shown here is a diagram that indicates how this library leverages abstraction and design to transition from lower level data structures for vectors, matrices, and other objects through algorithmic layers, which I'll discuss in a bit. So my particular focus in my career has been largely on nonlinear algebraic solvers, which then, of course, build on lower level capabilities for iterative linear solvers. So PETSI is deliberately designed to be composable, hierarchical, and extensible. And this has enabled the toolkit to be very widely used by a variety of applications and customized as needed. So this slide shows just a few of the many thousands of applications that have been built by using our software, PETSI. This slide, though, illustrates a more important broad point, and that is all of the math libraries have broad impact by encapsulating within their software the latest advances in applied math, algorithms, and data structures, and then in turn, serving the broad applications. So really, what we can think about over time is broad impact, not just of the library that I work with, but of hundreds of other ones within our DOE system. No single metric or even set of can fully explain scientific impact, but this slide conveys a few bits of information that can illustrate relationships within our computing ecosystem. So we have tens of thousands of users of the application, both people who use the application directly and some who use toolkits that have themselves been built on top of the application. There are many of those. We have many citations of the user's manual and website for the software, as well as many different external packages to which we interface. So PETSI has always been a strong innovator in leveraging and interfacing broadly among our own ecosystem. So this strong work by our community has enabled the team to win a variety of awards. We're most proud of our team awards, such as the R&D 100 award and recognition of our early paper as one of the 40 that have changed the face of science by the DOE Office of Science. We're also more recently involved in a foundation focus that is a nonprofit supporting open code for better science. We're designing software to work on the highest end systems, exascale systems, and also to function across the ecosystem of computing hardware, from laptops to mid-sized clusters, all the way to the largest machines. And we're especially looking at heterogeneous architectures that incorporate both CPUs and GPUs. So among the challenges that we and others in the community are addressing are these challenges with disruptive hardware changes, are increasingly deep memory hierarchies, very high node and core counts, and of course, the need to conserve power. As we're doing this work, we're addressing trends, which these days include the close coupling of modeling and simulation with large-scale data analytics, and increasingly AI and machine learning. So while we're doing all of this, we're working with phenomena that are multi-scale and multi-physics. And while we're doing so, we're considering the need for so-called outer loop optimization, sensitivity analysis, design, uncertainty quantification, and otherwise. While we're doing this, we of course need to have trustworthy science and the ability for reproducibility. So our opportunities as a community are to leverage new technologies that facilitate collaboration across our community with open source software. And as new capabilities in AI and machine learning are emerging, we also are doing research to figure out how to apply those in our world. This picture here is from a whole device modeling of fusion energy sciences. It's one of the many communities that I've worked with over the course of my career. So let's step back and put what we're doing now in historical context. Argonne has long been at the forefront of scientific computing and computational science. There's a fascinating read for any history buffs, a dissertation written by Charles Yu. I encourage you to find this. It's available as a book on Amazon. And this talks about the social history of computing, the people and science and the activity of computing in the early years. And more recently, a team in Argonne, including Paul Messina, one of our special guests here, and deeply involved in Argonne computing leadership and history, put together a history of the computing at Argonne. So some information about that is available on our website. Here's a timeline that shows that from the various early days when Argonne was founded as the first national lab in 1946 by Enrico Fermi, shortly thereafter, Argonne scientists built Avodac, the first digital computer at the lab. And ever since, Argonne's scientists have really been pushing forward in a culture of understanding architectures, heterogeneity, issues such as computational accuracy, precision, convergence, and so on. There's been a strong tradition of leadership throughout history, including in 1980s when Paul led the establishment of the Math and Computer Science Division. So I entered the scene only after all these great foundations had been set. But boy, was I excited to arrive on site at Argonne in the early 1990s and to have the privilege of working with leaders, in particular Bill Brock, who were at the forefront of establishing the message passing interface standard, or MPI. And that enabled us to develop our new numerical library policy to fully leverage that community standard. And of course, since then, there have been many other important programs, SIDAC, ECP, and others. So today, I'll talk about my own experiences being part of a research team at Argonne and other broader teams in the community. This slide shows some of the very important elements of DOE research labs that are just so important and so new. So in DOE research labs, there's an opportunity for individuals to identify a research need in the broad community, to build a small team to begin making some process, leverage the lab environment, to expand the team as needed, and to collaborate with others in the community. And meanwhile, while doing this, of course, the team continues to grow and expand. Staff can build skills and evolve in their careers, and research topics can continue to grow and change over time as science needs and technology needs change. So you could consider me to be a case study of someone who's moved all the way across from starting off as a student. Of course, there are hundreds of other people who have amazing accomplishments, both at Argonne and in the broader lab community. This slide are some fun word clouds, which I realize you can't read from such far away, but this is showing software and descriptions of software taken from teams who work in the directorate that I work in at Argonne themselves, the Computing, Environment, and Life Sciences Directorate. In August of 2024, we asked people to provide information about their packages in order just to get a broad sense of the topics that people are working on. Really an exciting, rich mix of software. And every lab has a similar mix of amazing software. This is my team, the Petsy team. Most of these people work part-time on our project. And in addition, we collaborate with others throughout the community. And one neat thing about Argonne is that it has been a host for many people who worked on this project. Some people have been staff and others have been students, visitors, and postdocs. So Argonne and DOE support in America software has been essential for work in this library. All of us have been working on long-term applied math basic research in algorithms and software for high performance computing encapsulated within this toolkit. Now, of course, there's so many different layers and levels of complexity in that broad topical space. What's shown on the right side here are just some of the interactions between layers of nonlinear solvers, linear solvers, and whatnot. The details aren't so important, but what is important is to recognize that we've worked really hard to create and design a scientific software library where we can incorporate mathematical understanding of the modeling, work with application teams to motivate and validate what we're doing so that we can make appropriate advances that can serve a broad range of needs, but yet be customized by particular scientific applications, and thus progress our software in a way that not only helps us do good research, but helps other people in science domains do their own research. So we recognize that there's no optimality without very deliberate, careful study and interplay among math, algorithms, physics, and computer architectures. So that's much of what the work of myself and the others in our numerical library community have been doing. My own work has focused on solving nonlinear systems of equations as represented here, where typically we have in current days systems of equations that are millions of degrees of unknowns or degrees of freedom. These are just two areas in which I have worked. Both of these have been supported through SciDAC, where we're looking oftentimes at Newton-Krylov solvers, where we have two levels of iteration. We're advancing the nonlinear solver, and we need advances in the linear solver in between, which are typically done through preconditioned Krylov methods. So we've worked hard to design software so that physicists can, or chemists or whoever, can focus on their application perspectives, but recognize that our algorithms can deal with complexities such as multi-scale, multi-rate modeling, a rich variety of timescales and nonlinearities, where we oftentimes need to consider broader issues in parameter studies, sensitivity analysis, and so on. So here we typically need support for user-defined customizations, because generally an off-the-shelf method might be adequate, but it won't be the best that someone would need for a particular circumstance. Next, I'll talk about pFlowTran as an exemplar application that is showcasing the synergy between advances in applied math research and then the impact on science domains. Now, I've chosen pFlowTran because it's an interesting one that was one of our first applications that built on top of SNES, the nonlinear solvers in PETSI, which is what I worked on. And of course, when we were first developing that capability, we were seeking users, and it's not always easy to convince users to use your latest new software. At the time, most users were more comfortable to work with lower levels of abstraction in linear solvers, but the pFlowTran people were very brave. That project started as a computational science graduate fellow program summer practicum led by Peter Lichtner of Los Alamos, who engaged Len Hammond and later Richard Mill to develop this application on top of SNES, the nonlinear solvers in PETSI. So it really does leverage not only the numerics, but also the lower level infrastructure for data structures and performance profiling and more. And pFlowTran is a massively parallel code for simulating subsurface modeling. Been used in many different application areas. And a key point that I want to emphasize is that the collaborations between Oscar researchers and the application science teams have really enabled us to push forward on both fronts. So the important motivation coming from the science teams has helped us know where to focus our work in algorithmic research. And then likewise, our advances in algorithms and software enable the applications to themselves progress further. This slide shows us some advances done a while ago with the pFlowTran team, where we employed hierarchical nested Newton-Krylov methods to overcome bottlenecks in synchronization that are very common in large-scale systems. This work has then enabled simulation at higher levels of fidelity, which has qualitatively changed what it was possible to model, as shown here on the bottom, where we have increasing model resolution as we move to the right, therefore enabling us to better understand flow, in this case, for a plume of uranium modeling. Of course, the needs of applications and the capabilities of our math always continue to grow and evolve. This slide shows that even now we're continuing to progress, and in particular, some of our team, Hong Zhang and Emil Constantescu, are pushing forward with some of our time-stepping adjoint methods, which are enabling us to then provide capabilities for first and second order sensitivity analysis. In turn, Richard Mills, as part of BES and BER partnerships, is revising pFlowtran to then use this new higher level of abstraction, TS adjoint, so that eventually this work will allow the use of online physics-constrained machine learning. So that is directly incorporating pFlowtran into the theory. So this constant evolution and change with new math research enabling new science is a hallmark of not just work by my team, but by all the math teams and other CS teams throughout OSCAR. This work, of course, is done in a community context. And this diagram here shows that for the work that I'm describing in Pepsi, we're considering developers who come from not only DOE labs, but also academia, industry. They may focus on algorithms, applications, but there's a rich and complicated intermixture and dynamics. We wrote about this in a paper, and likewise, other math libraries, such as those listed here, Hyper, Super U, Super LU, Sundials, and Trilinas, have similar rich interactions in their communities, and likewise, so do others in the broader scientific software ecosystem. This slide is way too detailed to attempt to read closely, but it is attempting to convey the importance of consistent investment, not only in base math research, but also in complementary application partnerships, advancements from new technologies, software ecosystems, and so on. So our team began in the early 1990s when Bill Gropp and Barry Smith began doing their own research in domain decomposition and created PETSI as a vehicle for that algorithmic research. I joined them in 1993, again, building nonlinear solvers as a vehicle for my algorithmic research. And over time, others have joined us, and we have progressed through continuing those algorithmic advances, partnering with teams through SIDAC and other mechanisms, and then more recently, getting support through the Department of Energy's exascale computing project to transition to fully exploiting GPUs for much faster performance in these heterogeneous architectural areas. So all throughout, our team has continually been reinvesting in ourselves and growing and changing. An area of exciting current work is part of Argonne's new base project, which is one thrust of a variety of activities led by Valerie Quay, director of the Math and Computer Science Division. For many years, I was PI of a composable solvers project that did much of the research just discussed. Now our base math projects are collaborating together in this synergistic way, and Toby Isaac is our thrust leader. So our team, including me, is working on figuring out how we can better improve energy efficiency of our algorithms so that we can continue to scale as needed to address next generation science challenges. So let's consider the timeline in terms of funding and activity. I've been supported by the base math program throughout my entire career, and I'm so grateful for that. Also, I have received funding from the SIDAC program for a variety of years through both collaborations with application teams in accelerator physics, nuclear energy, fusion, and I have participated in a variety of institutes and projects in math and computer science. All this background that I was able to build while a relatively early career person at Argonne laid a foundation for me to have leadership roles in co-organizing community workshops which we know in the Department of Energy are a great way to bring together diverse people with different perspectives to explore what really are the core challenges that our community need to address in the future. And these pictures are the covers of reports of several workshops that I co-led. One about integrated fusion simulations, another about multiphysics simulations more broadly, and two others that focus on software productivity and also the science of scientific software development and use. Now, each of these reports is very interesting and very detailed, lots of insightful analysis, but I think we could really boil down much of what's in all of those reports and many other reports into two comments that I'll show on this slide. So just take a moment and read this quote by Sir Arthur Stanley Eddington. This is a quote that my collaborator David Keyes discovered when we were working on our multiphysics workshop. And I think it's so important to recognize that when we've studied one item, whatever that might be in software modeling, analysis, or simulation, we might think that we can know how to handle two, because two is 1 and 1. But actually, we still have to recognize the complexity of studying the concept of putting those together, and what's meant here by the word "and." So many complexities in multi-scale multiphysics modeling and other areas of analysis and design. And then building on that concept, it's important to recognize this quote by Steve Jobs from 1997, and that is, the way to achieve programmer productivity is to eliminate lines of code that you have to write. Because of course, no one person can write all the code for everything. Not even one team can write all the code for what is needed to do. So we need to figure out how to develop robust ecosystems so that we can address our most challenging science problems. The Exascale Computing Project recently concluded in December 2023. This is a groundbreaking project across many parts of the Department of Energy, which brought together many teams, many collaborators to address building exascale environments that could solve science problems. I had the privilege of serving as the Deputy Director of Software Technology for the time 2000 through 2003. And I worked with this team of people shown on the bottom. The directors of ECP over time are listed on the top, including Thomas Seaman, who's here with us today, Doug Cothy, former director, and Lori Dyson, the director toward the end of ECP. So all of us and the teams who worked with us collaborated to advance science at scale. And one way to think about this work is to consider, from the software technologies point of view, that we worked to build an ecosystem consisting of 70 distinct software products across a variety of technical areas, where we built capabilities that then served 25 applications in ACP across a wide variety of science domains. We did this, of course, with the intent to fully leverage and exploit all the power in the new exascale computing environments. So working together as a team of teams, we built on individual software products, which I just discussed as an example, and built together collaborative sets of products that are complementary. Math libraries that I just mentioned is one. There are others in development tools, programming models that run behind data and biz libraries, and so on. And then built on top of those a more cohesive extreme scale scientific software stack. This concept of E4S is led by Mike Carew, who's the director of ECP Software Technology. So some of the values brought to the community by considering this approach are building up community policies that jointly different researchers worked to develop to make sure that we could overcome barriers that had prevented our software from being used in combination. We also developed capabilities that enabled more easy testing and installation of software and reducing times for applications to be built and installed in different areas. So as we're moving forward, we're continuing to grow on this foundation. That's led by Samir Shende at the University of Oregon. And also we leverage SPAC, which is a product led by Todd Gannett of Livermore. So we're developing new capabilities that are leading us into the AI future, where we're combining modeling and simulation and AI. This slide shows one example of how our advances here throughout the math library community have helped us progress in addressing issues in algorithms, performance, coupled simulations with multiphysics, multi-scale modeling, and so on over time as we're working towards advancing predictive science. So within the exascale computing project, Mike Carew and I started the XSDK prior to the beginning of the exascale computing project. And then during the lifetime of ECP, I led the exascale. I led the XSDK for several years before transitioning to my role as Deputy Software Technology Director. And toward the end of ECP, Ulrike Gang led the project. So we transitioned from our initial work, which dealt with just 4 software libraries that were overcoming challenges in subsurface flow that needed to use Hyper, PETSI, Super LU, and Charlinos, to building up a context of 26 math libraries that all agreed to follow community policies and a variety of applications. So this is just one example in one sub-community of our work to advance software ecosystems. This work, of course, has required the combined contributions of hundreds of people with very diverse skills, including applied mathematicians, application scientists, data scientists, performance engineers, research software engineers, cognitive and social sciences, and more. And this slide is really showing how all of us within the exascale computing project especially, but other projects as well, work together as aggregate teams. That is a team of teams, which exemplifies our multi-layered collaboration throughout the community. Elaine Rayborn, a social scientist at Sandia, one of our project members in the Ideas Project, who has helped us understand and pursue more work relating to our aggregate team analysis. So we recognize that in order to do outstanding computational science, we really need to have awesome software. It has to be totally trustworthy, high quality, and we recognize that only by directly investing in that can we meet the challenges of the day in scientific computing. The Ideas Project, which my career and I started in 2014, has been a catalyst for advancing community attention to improve software productivity and sustainability by fostering software communities, by drawing attention to the importance of improving software practices, and then disseminating knowledge. So we believe that moving forward, even more attention is needed on this area. And in particular, we need research software science. This is a term that Mike Carew has coined to talk about hypothesis-driven science that can help us do better research with our software. A recent workshop done in 2021 summarizes some of the challenges in scientific software development and use, and we advocate for continued investment in this work. Our community has achieved strong advances through the exascale computing project by advancing science to use new exascale machines and develop a software ecosystem. Going forward, our community is facing new challenges, especially as we're trying to figure out how to leverage AI and machine learning while also integrating modeling and simulation. So this screenshot shows a community report where many of our community leaders are figuring out how to chart a path forward. One aspect of work post-ECP that some in the community are involved with is establishing a new consortium called CAS, the Consortium for the Advancement of Scientific Software. CAS brings together a set of teams post-ECP who are focused on advancing a variety of different aspects of the software ecosystem. The CAS consortium is led by David Bernhold at Oak Ridge and supported by team members from throughout a variety of labs. So I'll talk just about PESO. It's a project that I lead with my crew, but I'll just mention that likewise, other projects are focusing on other parts of the ecosystem. PESO is looking at advancing partnerships, services, and products that help propagate forward the notion of a scientific software ecosystem, especially to serve the needs of science as we're moving forward in an age of combining simulation and AI. The benefits of considering this software ecosystem approach we've talked about already, but are summarized here on the right side of this slide. So some key benefits are technical, that is advances in coding by being able to leverage other folks' code, but also some are more community oriented, where we're building up community teams and members who can make advances together. This slide is a screenshot of our CAS website representing our consortium, and it just showcases some of the benefits to applications shown here: fusion modeling, particle accelerator modeling, where we're using a variety of software products from throughout the scientific software ecosystem, all the projects and areas that are supported through CAS, as listed here on the right. And now going back to the timeline, I'll just mention that moving beyond the first part of the timeline that we discussed has gotten us into the area where my work has been funded through ECP, as well as through funding from Oscar and BUR in collaboration on the Ideas Project. Now we're in an era where we're having some funding for software stewardship through the Next Generation Scientific Software Technologies program, and we're looking forward to new opportunities through AI for Science, where now I'll talk a bit about new work that I have the privilege to explore through this fellowship. I'm working with a team to look at next generation ecosystems and how, in particular, we can take a holistic approach that combines community, software, and AI for cross-disciplinary team science, especially as needed to advance in DOE mission areas. So we're looking to explore the current state of collaborative team software in scientific computing, with emphasis on how emerging AI technologies are impacting that and what really are the driving needs of cross-disciplinary collaboration. As part of this, we're exploring the use of generative AI in team-based software. So here's an example where we could ask ourselves, how might AI assistants help in the process of doing numerical library research? So with our team, we are looking at how assistants can help us in understanding and executing the tasks that typically we as people have always been doing. So these are just some of the areas, and here's some ideas about how AI assistants might be able to help. So there's a lot of them, and we are just getting started with this work to look at some of these areas. We're collaborating with some folks within ALPI, Argonne's Leadership Computing Facility, to build some PETSI AI infrastructure, where we are considering how to leverage existing large language models, but build capabilities that help to provide more specific information to those LLMs so that LLMs can do a better job of working to help with tasks that are very specific to our library and our scientific needs. So the details of this diagram really aren't so important, but the key point is that there's a need to interact and do some fine tuning or retrieval augmented generation in order to get better output that can help us scientifically. We're working on some case studies. Here is one that's showing the use of fine-tuning training and retrieval augmented generation to improve the responses of LLMs to specific questions that relate to Krylov methods. And we're in the process of looking at various approaches, various large language models, embedding approaches, and whatnot. This diagram shows the improvements where we've been considering for particular questions, whether there is an answer that makes no sense, it gets a score of 0, an incorrect or inaccurate answer, which gets a score of 1, basically correct material with minor inaccuracies, level 2, a correct and clear answer, level 3, or an ideal answer. So what we've been finding is that we have made some progress, but there's a lot to still do and learn. So right now with our, we've been able to get good quality answers for many questions, many improvements, but still much improvement to do. So here's an audience participation part of the day. So if you've been snoozing, this is the time to wake up. I realize this text is small, so I'll read it to you. So there's a question for you. What does KSP verb do? So if you're an LLM, what would you say to that? Well, a particular LLM responded and said, KSP verb is an implementation of Krylov subspace method in PETSI to solve systems of nonlinear equations. It's a block version of the unreconditioned Richardson method. Not as widely used or advanced as others, but it can be usable in certain contexts. Okay, question. Where do you think this would rank on the scores? Is it accurate or not so accurate? All right, it's a hallucination. This is not true. This is not a thing at all. It's just a made up word. But, you know, it just shows you some of the pitfalls of what LLMs can provide. So after doing this, this finer training, we got a much better answer that explains you must be having a typographical error or misunderstanding. So this is just one simple example, but you know, it's good food for thought as we're working to figure out how to advance in using AI more generally. In this work, we're collaborating with folks at the ALCF, the Argonne Leadership Computing Facility. We're using some of the specific AI technologies, and as we move forward, we plan to use more of them. So ALCF is really helping push forward in our community the concepts of integrating simulation data. So in conclusion, I would like to emphasize the incredible importance of DOE investments in applied math research, more broadly OSCAR investments in computational science, computing sciences, computer science. The basic science research that we as a community do in OSCAR pays dividends, of course, in math and computing, but then also it enables translational science progress across countless domains. So here today, I've talked about my own work in composable solvers in advancing algorithms in numerics, especially within the PETSI and TAL libraries. I've also talked about the importance of scientific discovery through the SciDAC initiative and other partnerships, which promote multidisciplinary collaboration across domains, spanning applied math, computer science, and various application areas. I've talked about the importance of broad community projects, such as ECP, where we've learned how to go after big, bold objectives while pursuing cross-disciplinary team science at scale, and how to build research ecosystems for scientific software. And as we move forward, we have lots of challenges, but I think as a community, we're well poised to address them by looking at how we can progress to build the next variants of scientific software ecosystems, especially those that couple modeling and simulation on high performance computing systems with AI. And to do this while harnessing our full community, our software, and fully recognizing what AI capabilities we need to tackle mission-driven team science. So I'll just end to say thank you. These are just some of the wonderful folks I've collaborated with over the years. There are many others who could not fit on the slide, and I want to thank all of you. for your support, for your support as sponsors and collaborators and friends.
Thank you very much for a really exciting lecture. And I've discovered we have some more things in common. We both went to University of Virginia for graduate school. I didn't know that we both started out at small liberal arts colleges in Pennsylvania on our path to the University of Virginia. So at this point, we're going to open up for questions both in the room and online. And Dr. David Rabson from the Advanced Scientific Computing Research will be monitoring the online questions, and we'll turn to them after we take a few questions from in the room. So, questions? Yes.
So I resonate with your early experience of going to a lab and discovering the passion, the activity, everything that goes on in a lab. So I would like to see if you can expand a little bit on that and use this information, what you learned then, in order to inform what you're doing now and what maybe the community can do to attract more talent to the labs.
Oh, that's a great question. I personally feel that exposing opportunities for impact, explaining the excitement of the mission of the Department of Energy Science can really engage so many people in then wanting to do whatever element of work is at the labs. In our particular case, it's scientific computing. We've had some good examples where we've shared and recruited people focusing not just on teaching them the nitty-gritties of math and computer science, but really focusing on the why. What science can you do? How can you advance basic science? And I think that tends to really be a powerful motivator to engage people and in seeing the beauty and the opportunity in advanced scientific computing. Too often, I think, many of us tend to want to do tutorials and teach about our work from the fundamentals of what it is, which many of us find very beautiful, the details of message passing code, or the details of convergence analysis for algorithms. And that certainly has its place, but I think also speaking to the opportunities for impact in basic science research is powerful.
So as we all know, AI these days, there's a lot of hype in the kind of the various Congress, etc. How would you kind of describe the role of basic science AI in improving AI algorithms? I always struggle with that message when I'm talking to other areas that work in a more applied AI.
Yeah, that's a great question. I think our whole community is trying to figure out how to answer that question. My view is that we're really in an exciting time of rapid learning and rapid change. And we as a community have the opportunity to dive in and explore and learn how to make progress. I personally see a lot of opportunity in combining AI capabilities to help us really engage people more effectively, to focus on the basic science impact opportunities and help us as a community do a better job of managing complexity and change in the intermediate layers of infrastructure, which right now are very complex. They will continue to be complex, but require literally weeks, months, years of time to invest in order to understand how to make progress and impact. So hopefully AI technologies can help in some way with all of that, as long as we do the research to build appropriate scientific based elements that address gaps that are not being addressed in the mainstream technologies.
Through your career, have you noticed that it has become easier and more accepted for teams of mathematicians, computer scientists working with, we sometimes call domain scientists, chemists and physicists, I asked that question because for AI, of course, that will be even more necessary or more useful than it is now. So in your 30 or so years, has it gotten to be easier or not yet?
Well, I think that's a great question. Oftentimes, common interests really drive the most successful collaborations. And I've seen that partnering across domains can be incredibly powerful and work really well when they're natural drivers for that. So I think the combination of having really compelling natural drivers where we're advancing basic science in important ways for our nation, combined with sustained funding for that will, really makes a difference. We need it both.
I think we'll, any online questions, David?
Yes, yes. The questioner has a long prelude about particular recent acts. But if I can summarize the question, can a software bill of materials improve cybersecurity?
Well, certainly, software bill of materials are an important aspect of understanding and communicating about approaches in scientific software. So I think we as a community need to address this in a very rigorous way. And software bill of materials is an important part of potentially a variety of approaches to make sure that the software we're developing is robust, trustworthy, and performing as expected.
Other online questions, David?
There's quite a few. Let's see. How do the next generation of math and computer science grad students get involved in scientific computing research that happens at labs? A lot of times seems to very heavily delve into software development and maintenance.
Well, I think that's an important question. How can we engage the next generation of students in our work in scientific computing? And I think that's a complicated, multifaceted answer. Certainly, the Department of Energy has supported a wide variety of educational and outreach programs that have been incredibly impactful, and in fact enabled me to begin working at a lab when I was a student. So I'd say continuing strong support for those educational programs are really important. Also providing means for the scientists at the lab to engage with a wide range of students and explore common interests is very important. I think by making sure that the choices for particular students working with particular scientists on particular projects can make such a difference, so that if there really is true alignment and interest and background, can have much larger chance for favorable outcomes than without that.
Yeah, one more.
Can you comment on the distributed nature of the PETC team? Was that helpful to the effort?
Teams these days, I believe, very naturally incorporate distributed elements. I'd say when the PETC team started, even before I was involved, it included two people who happened to be at the same place, Bill Grapp and Barry Smith. And then I arrived and there was three of us. And then we recruited Satish Ballet, who's been with us forever. And there were four of us. And then over time, we've gradually engaged other people. And many of those, I'd say no matter where people physically reside, there's been strong interactions in person, typically, in order to build understanding, build relationships, and build trust, and then also make community decisions on what work to do. So I'd say even now, as the team is distributed, we come together regularly through both in-person meetings. There's an annual PETC user and developer meeting where people from all over the world come together and meet one another. And then there are also regular meetings for various aspects of development and community work. So I think a hybrid mode is common in many team collaborations and can work very effectively, but I think the in-person interaction at some level, at some times, is really important.
I'll ask one final question. The whole concept of team of teams, I thought was an intriguing one. As you look forward to the challenges in your field, what's going to be the next big advance that requires team of teams, teams of teams?
Well, I can imagine all sorts of scientific computing projects that we as a community could undertake. And deciding specifically where to focus, of course, is a challenge, not just for me, but for all of us jointly to determine. It's clear that leveraging artificial intelligence for science to help us advance our science goals is a current opportunity that's incredibly exciting and also timely and urgent. So I would expect that will be an area of focus for many people.
Yes, I concur. Lots of challenges out there. Let's say one more round of thank you. I'd also like to acknowledge that Scientific Computing Research, who made all the arrangements for this particular event. And of course, Katie Schroeder-Spain, who from the Deputy Director of Science Programs Office runs this whole awards program and provides us with the guidance that we need to successfully carry these events to successful conclusion. So thank you very much, Katie, much appreciated. So it's been great hearing you today. I've enjoyed all four of these lectures now. They've been great and computing is sort of part of it. It speaks to me as an experimentalist who actually has a bachelor's degree in math, but about how we bring together that interface of the computational piece, working with the experimentalists, working with the user facilities, whether they be computational or experimental. So really great lecture. Thanks so much.
Thank you.